Professor Tess Lloyd from MIT. You're still belonging to Department of Mechanical Engineering?
Absolutely.
Okay. And you're here till Friday.
Yes.
You've already visited Tokyo Nikka Daigaku.
Yes.
And NII.
Yes. Tomorrow's Todai.
Tomorrow's Todai.
And then Tokodai.
And Tokodai. And you'll be giving 4 talks.
Yes.
In 2 days.
Yes.
And then,
as usual.
And then you'll move on to Kyoto.
Yes.
For a conference workshop on quantum information and quantum gravity.
That's right.
Okay.
You're right. You're right on.
So far, I did okay. Maybe you should introduce the rest of yourself.
Thank you very much, Kohei. It's a great pleasure to be back here at Keio University. I thank Ito Sensei for inviting me here. I love coming here because every time I come here, I learn all kinds of awesome new things that are going on from the students and postdocs here. And after I give my talk, I'm looking forward to hearing from you about what you guys are doing. So my talk today is about quantum machine learning. Oh, and by the way, I know that I'm a special honored guest because Ito Sensei is allowing me to use the very precious chalk, of which there is almost none left. You know, chalk is, after all, a scarce fossil resource made out of tiny sea creatures. There's only so much of it around, but there's very little of this amazing chalk around. So, quantum machine learning, what is this about? So how many people here have a background in quantum mechanics, have studied quantum mechanics? Okay, how many people here have not studied quantum mechanics? Okay, and how many people here, this leaves some people who apparently both have and have not studied quantum mechanics, because not everybody raised their hand, which is, these are the real quantum mechanical people. So, since most people here have studied quantum mechanics, I won't say very much about quantum mechanics just now. Of course, quantum mechanics is the branch of physics that deals with things at their smallest and most fundamental. Instead, I'll talk a bit about machine learning. So how many people here have studied machine learning? A few people. Good. And luckily one person who's not studied quantum mechanics has studied machine learning. So probably you know more about machine learning than I do. But for the people who have not studied machine learning is a branch of computer science that tries to take data and find patterns in this data and do this automatically via machine. So machine learning consists of a set of algorithms that analyze data and try to find patterns in the data. For instance, a very common form of machine learning is voice recognition. So voice recognition software, like the kind you know that you have in your smartphone, it listens to what you say and it tries to interpret this as words or in Japanese or English or whatever language you're speaking. Actually, voice recognition software has gotten much, much better. I remember back in the late 1990s at MIT, being an institute of technology, they are often early adopters of technology. For instance, has anybody here, who has been to MIT? I know you have been to MIT. So if you go to MIT, you enter in the main entrance through an automatic door. And the automatic door is the world's oldest still functioning automatic door. It was adopted as a technology in 1915 there. Of course, this means it is often broken. So in the late 1990s, some clever professor of computer science at MIT convinced the administration to fire the people who were answering the phones. So previously, you would call up and you would say, I would like to speak to Jane Smith. And a human being would say, why, yes, I will connect you to Jane Smith. And then you'd be connected to Jane Smith. Okay, they fired all these people. They replaced them with voice recognition software. And for the next 5 years, you would call up and you would say, I would like to speak to Jane Smith. And then this computerized voice would say, now ringing Mary Lefkowitz. If this is not the right number, press 9. Beep. Jane Smith. Now ringing Hua Zhang. Beep, 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 beep. So it didn't work very well, and it was incredibly annoying. But now, however, you know, we're 2 decades later almost, and now actually you find voice recognition software works a lot better. So most of the time it works quite well. Indeed, it can start to as it learns from you, your smartphone will get better and better at recognizing what you're saying. And so voice recognition software is now much better. So what happened? Actually, the primary algorithms for machine learning, many of them were developed back in the 1970s and 80s and 90s. And they didn't work very well, as I just described. For example, a common form of learning is based on neural networks. Neural networks, artificial neural networks, were actually invented in the late 1950s, and then there were lots of advances in the 1980s, and then they stopped working very well. And I remember around 1988 or 89, I was a postdoc at Caltech, and I went to go talk with John Hopfield, because I would go and talk with John Hopfield because he was a very interesting person, one of the pioneers in neural networks. And he said, you know, I know that these things are not working so well right now, but if we only had computers that were 1 million times more powerful, and if we had 1 billion times the amount of data, this would work, I swear. Okay? Well, now we have computers that are 1 million times more powerful, and we actually have 1 trillion times the data, 10 to the 12th times the data we had back then, and now a lot of these methods are working very well. This is not to say that there haven't been a lot of really great advances in machine learning since then, but I think at bottom, one of the basic reasons that these methods are working well is we have a lot more computing power. We have much bigger training sets on which to train these algorithms. Nonetheless, you can only go so far with computing power because the amounts of data are growing very, very fast. Then the kinds of algorithms that one constructs, they start to run out of steam at a certain point because, as we'll see, it still can be very hard to extract patterns from large data sets. And here's where quantum mechanics is going to play a role. So what I'd like to do in this talk is to present to you, I'll describe a bunch of classical machine learning algorithms. These will be very simple, straightforward versions of these algorithms. And then I'm going to argue to you that if we could build an even quite small scale quantum computer, one that say had a few hundred quantum bits and could perform around 10,000 operations coherently, which actually is the kind of quantum computer which we're likely to have over the next 5 to 10 years. If we had even a small-scale quantum computer, that it could do much, much better than large-scale classical supercomputers for a variety of common machine learning algorithms. And I'll describe why that's true in just a second. So let me show you. Let me now give a couple of examples of the kinds of things that you might want to do with machine learning. So examples. So machine learning, by and large, the problems fall into 2 categories. So one is supervised learning. So in supervised learning, for instance, you're given a bunch of scrawled examples of the letter 5, and scrawled examples of letter 7. Handwritten examples, I know they're hard to see, right? That's the whole point. You're given a whole bunch of examples. You're told these are 5s, these are 7s. And your goal is to classify, when you're given a new squiggle, is it a 5 or a 7, right? So this is a very common kind of problem. Now you'll see why I'm using the fake chalk for this, because the kind of problem like this is we're given if you think of this, we're given a couple of clusters of data, and now somebody presents us with a new datum. So here's a new point, and the question is, do we assign it to this cluster or to this other cluster? So in general, our data is expressed, so our data is given to us in the form of, say, a bunch of vectors. these vectors are going to belong to some high-dimensional vector space. They could be very high-dimensional. So for instance, in the case of this, what I could have is I have the vector is I have a set of pixels, so I have a pixelated version of these 5s. There's a certain number of pixels in this box. I have, you know, white pixels for the background and black pixels for the where there's a mark. And so each of these numbers or examples is a vector in some high-dimensional vector space. And if you have a notion of a distance, then you can compare to see which vectors are closer to each other. I mean, in a simple example of a distance, so this is a distance, is something like just the norm. Something like that, right? This is the kind of thing that we have. Okay. So here's a particular algorithm that I'm going to tell you about. All the algorithms I'm going to tell you about here, the classical algorithms, are ones that have an exponential speed up when you do them quantum mechanically. So this first algorithm is an algorithm where the idea is what you do is you construct the optimal separating hyperplane between these pieces of data. So they sit in some high-dimensional space. So I construct a plane, and the idea is that I want to construct the plane that maximizes the margins between the plane and the data, right? So my goal is to construct a plane. So here we're going to construct optimal separating hyperplane. And then, of course, if we find, here's our datum, if it's on this side of on the blue side of the hyperplane, we simply assign it to this cluster right there. And this is for historical reasons, this is called a support vector machine. Okay? It's called a support vector machine because these vectors that lie on the margins are called the support vectors. And so this is a method for constructing a device to discriminate if I'm having a supervised learning problem that gives me, in some sense, an optimal form of discrimination. Support vector machine is a very common kind of method that's used in machine learning historically. Okay, now, this already should give you a hint of why quantum mechanics might be helpful. Because my data is expressed in the form of vectors. I have some kind of distance right here. And actually, the problem of constructing this optimal separating hyperplane is just some problem in linear algebra in a very high-dimensional vector space. In fact, you can end up phrase this, you can construct some matrices that correspond to the data, and then you can construct this as a matrix inversion problem in a high-dimensional space. So it's just a problem in linear algebra. Another type of, so is this clear? What's going on here? This is a very common kind of machine learning algorithm. Then there are unsupervised problems. So here, the problem could be that I have a bunch of data, and I'm not told it falls naturally into clusters, but I'm not told what the clusters are. So I want to identify the clusters of data, which here are kind of obvious. I want to find out how many clusters there are, and then I want to be able to assign things to the clusters. Okay? So you see the difference is that here I'm told that these are 7s and these are 5s, but here these could actually be, I could just be given a whole bunch of examples of handwriting for digits. I'm not told that there are 10 digits. I'm not told what they look like. And then what I'd like is I'd like to have an algorithm that will naturally find that there are just 10 classes here, and then assign things to these different classes. Okay? So a very common algorithm for such unsupervised learning is what's called principal component analysis, whose acronym is PCA. So in principal component analysis, the way that this works is I construct a covariance matrix. And my covariance matrix is just the following object. I construct it out of the data. I just take these vectors. I multiply each vector by its transpose. This is a matrix. This, by the way, you can see that something, if you want to think of these vectors, I'm going to give hints about the quantum mechanical part of this. If you want to think of these vectors as being states of a high-dimensional system, so a high-dimensional quantum system, you may note that this is essentially the density matrix for these vectors of the system. See, I'm hinting at what's going to happen here.
But how do you actually define bases? If they're like, for example, you have many dimensional vectors, right?
Right. So here I gave a natural way of describing it in terms of each one is just a vector of zeros and ones, just given by a raster scan across it. There, of course, a lot of work goes into saying what is the best way to define bases. I mean, so anyway,
how difficult that is in terms of setting the bases classically versus quantum mechanically. I wasn't sure because once your bases are set, you can define density matrix and everything.
Yeah. So I mean, first of all, you don't have to. The nice thing about methods like this is the hope is that such methods will be relatively basis independent. Right. So if I just have a raster scan of these, and then things that look like each other are, in some sense have a reasonable overlap, then you hope that that's pretty good. Right. But of course, there a lot of effort goes into massaging the data to find the right way to represent it in the future, in the first place. I'll talk a little bit about that in a second, right? I mean, data is information about stuff that's out there in the real world, right? So it's information that was collected about real things. And then what one hopes is that if you do this in the right way and define a distance, that somehow the distance in your data reflects in some sense some natural distance between objects out there in the real world. But of course, just the act of collecting the data distorts the relationships between objects in the real world. So a lot of effort goes into that kind of thing. Anyway, the covariance, so principal component analysis, you construct this covariance matrix. A nice data set for this, by the way, would be financial data sets, okay? So these V's could be, for example, each V could be a gigantic vector which represents the changes in stock prices over a 24-hour period. In all the stocks in the stock market. This is a very high-dimensional vector. The J could sum over different 24-hour periods. And then this matrix, this covariance matrix, will give the correlations between the prices of the different stocks at different times within that 24-hour period. I mean, if you look at what this contains, so each component, I will take something, I'll have something like V sub I, or I'll call it V sub K, sub J, V sub L. So I'm looking at, this would be a term that's in the sum. It represents a correlation between the kth value, this stock K and stock L at different times. So this covariance matrix represents correlations or covariance in the data. And people who analyze financial time series want to find if there are simply expressible correlations between the data. I mean, there's a lot of money in this, okay? So in principal component analysis, what you do is you diagonalize C. And you say C is equal to the sum over K, P sub K, and you find a set of vectors, which I'll just call W sub K, W sub K dagger. And if only a small number of the P sub K are big, are much bigger than 0, okay, then it means that C is effectively low rank. And the corresponding omega K are the principal components. So, for instance, if it turns out that all the motions of stocks, of all the different stocks in the stock market, are highly correlated with each other, and there's only a few forms of correlation, of ways that they can be correlated with each other, then this matrix C will be effectively low rank, and it will have only a few principal components. You see also that this principal component analysis is a way of compressing the data, right? If there are only a few principal components, that means that all the vectors in my data set can be written just as a sum of a few W's. So this is actually, you can think of principal component analysis as a way of finding the underlying patterns in the data and also giving you a method for data compression. And it's based on simply diagonalizing the covariance matrix in this case. There are other matrices you can associate with data, but this covariance matrix is a very common one. So you see once again that principal component analysis is an exercise in linear algebra on very high dimensional vector spaces. Okay? And let me just mention one more. This is one of my favorite ones in forms of machine learning. I've been working on it a lot the last couple of years. So, and it's based on looking at topological features of data. So, you see why I'm not using the good chalk for this, right? I just wanted to point out. I didn't want you to freak out. Okay, here's some data set. It has a hole in it. There is a hole in the data. Okay, pretty obvious if you look at it. But how do you figure that out? Okay, if somebody gives you this data, how do you figure out it as a hole? Actually, if I look really close, it's all holes. It's nothing but holes. Okay, but then if I kind of go further away and sort of take off my glasses and fuzz things out, then since my eyes are pretty bad, it's like, oh wow, it just looks like an object with a hole, right? And then if I go even further away, it's just, wow, it's just some kind of fuzzy blob, I can't see anything. So these topological methods, for machine learning extract topological features of data. And these are actually rather beautiful and elegant forms of data analysis, but they also rely, the way that they work is that they take these data sets, they take these very high dimensional vectors, they map it to an even higher dimensional vector space, and then they do algebraic topology. And algebraic topology, as its name suggests, is once again about doing linear algebra on very high dimensional vector spaces. So there are a whole bunch of machine learning algorithms that rely on doing linear algebra on high dimensional vector spaces. if you look, you know, you take a machine learning algorithm, you open up the hood, you see how it runs, you find that in a large set of examples, that the kinds of things that you need to do for machine learning, so the methods are things like fast Fourier transforms, plus eigenvalues, and things like solving linear sets of equations or performing matrix inversion. So inverting large, sparse, or low-rank matrices. So that's the kind of things that lie under the hood of many machine learning algorithms. And once again, to give you a hint, if you actually look at these three processes, fast Fourier transforms, finding eigenvectors and eigenvalues, and matrix inversion, you may note that if you're familiar with ideas of quantum computation and quantum information, these happen to be procedures for which there are quantum algorithms that perform exponentially faster than classical algorithms. And that's what we're going to use here to construct our quantum machine learning algorithms. And the corresponding algorithms are going to be exponentially faster than the classical versions. But before I actually go into details of how you do this, are there any questions? This is the end of the introduction about machine learning. First of all, machine learning person, is this okay by you so far? Are you all right? Okay, good. I haven't, I should say that I didn't, when I started working on this problem about 3 years ago, when my postdoc, Patrick Rebentrost, who came up with this idea of doing quantum machine learning, came into my office and said, Seth, we should do quantum machine learning. I said, great, what's machine learning? So all the things I've learned in machine learning, I've learned in the last few years, okay? So I'm quite capable of saying something wrong or inaccurate here, but I'm getting better. But for the people who are not, you know, haven't studied machine learning, does this make sense? It's amazing the number of machine learning problems that fall under these kinds of categories. A famous one, for example, is the Netflix algorithm. You know, that Netflix takes its gigantic database, they ask, okay, they look what people liked, and then they look what you liked, and then they're going to recommend another movie to you. This is a so-called matrix completion algorithm, and they actually do it using principal component analysis. They, on a daily basis, they recalculate the principal components of the covariance matrix for all Netflix users all over the world, and then tomorrow they use that actually, having constructed these principal components, they look at, you know, your overlap with a particular principal component, and they say, well, this person likes really schlocky horror movies, and we're going to recommend them this one. By the way, we actually did recently, as part of this effort, we came up with a quantum version of the Netflix algorithm, and we were excited because we could write a paper called the Quantum Netflix Algorithm. But then I Googled quantum Netflix algorithm. It turns out that Netflix itself calls its algorithm the quantum algorithm, even though it has nothing whatsoever to do with quantum mechanics. They just like call it quantum because it sounds sexy. And in fact, Hartmut Neven, who runs the Quantum Artificial Intelligence Group at Google, since Google has a Quantum Artificial Intelligence Group that studies a lot of problems about machine learning, he went to Larry Page and said, okay, Larry, we're the only people in Google who get to use the word quantum because we're the only people actually doing quantum stuff. So Larry Page said, okay, nobody else in Google can use the word quantum just to make it sound sexy. Okay? All right, good. By the way, there are also some very interesting algorithms. These are very commonly used these days. And in fact, many of these voice recognition algorithms and lots of pattern recognition algorithms work with these. They're called deep learning algorithms. If I have time, I'll talk about them for a bit. But let me just describe to you what these are. This is actually these are very interesting from the quantum mechanical perspective, because it turns out that places like Google and D-Wave are building large-scale quantum devices that are perfectly set up to do deep learning, or in this case, deep quantum learning, which sounds really great. So let me just tell you a little bit about deep learning. I may or may not have time to get to this, but I think it's important to mention this. So when I first heard about deep learning, I said, wow, this is really fantastic. Who knew that computers could learn deep things about the world, like computers will be telling us about, love and truth and happiness and life. It turns out this is not the case. It's actually, you have deep learning refers to the fact that you have a deep network. Like, for instance, a neural network in which things are connected at different levels. There are many connections in this, and there are many layers. So, many layers. And then that means that it's deep. That's what deep means. Sadly, it doesn't mean, life and love and truth and happiness and all that stuff. But I'd just like to point this out because, in fact, a common deep learning method, which maps very beautifully onto physical systems, is a so-called Boltzmann machine. And in a Boltzmann machine, I'll even tell you the quantum version of it, but in a classical version, each one of these is a bit or a spin. Each one of these connections is an Ising-like coupling. So I have something like this, so I'll make it quantum mechanical from the get-go. Omega I, sigma z I, and then we have plus gamma ij, sigma z I, tensor sigma z j. So it's just an Ising model, and your goal is to tune these weights, the energies and the couplings, so that the low energy states of this system recreate the statistics of the data. For instance, down here I could have these scrawled 5s, 7s, 9s, 0s, etc. And up here I could have something that says it's a 0, it's a 1, it's a 5, it's a 9. So this is called the visible layer. These are called hidden layers. And this is called the classifier layer. So the goal in constructing these Boltzmann machines is to construct a physical systems whose actually thermal states, so this is our Hamiltonian. So if I construct a so-called Gibbs distribution, which is a thermal distribution for this system, the goal is to construct a physical system whose thermal states actually match the statistics of the data. And by matching the statistics of the data, what it means is that if I say, okay, I make this bit, the 0 bit, a 1, and all the rest of these zeros, then what shows up down here are the samples in the data that are supposed to be 0. If I make the 5-bit 1 and all the rest of these zeros, it means I should get things down here, things that look like 5s. Conversely, if I set the visible layer to something that is a 5, then what I want is only the 5-bit up here should be a 1. So you see, this deep network is supposed to construct the proper correlations between the classifier labels and the data. And there's some very powerful techniques for training such deep networks actually to recreate data and to recreate these correlations. And just to make this quantum mechanical, let me note that I could also add things like I could add an alpha I sigma x sub I could add a kappa ij sigma xi tensor sigma xj. Now I've turned this from being a classical system, which is an Ising system, into a quantum system, which is an XZ system. And these kinds of systems have very complicated quantum mechanical correlations. And so it's perfectly natural to ask if I could construct a quantum system with these kinds of weights, can I actually have the quantum correlations between the data and the classifiers be given by the quantum correlations in such a system? These are exactly the kinds of systems that places like Google and D-Wave are building right now with thousands of quantum bits. Okay? So this would be deep quantum learning. Okay. All right. So that's the end of the introduction. I mean, I already took up half the talk giving an introduction, but actually I think that's good, right? Because in this particular topic, understanding what's going on is important. Actually, I think that's true for all science. And because people who might not have a background in deep learning, I thought that I would just tell you a bit more of this. So are there any questions about this before I erase all this stuff right here, or while I erase this stuff? Do people have questions or comments they'd like to add?
So how do you define, for example, 5 in a digital layer, in a quantum bit sense?
Well, again, it's just a string of zeros and ones, right? It should just be pixels, right? Yeah, it could just be pixels. Yeah. Exactly. And in that case, you'd like, I mean, in the quantum sense, you'd like to create some kind of quantum system that correlates, you know, it could be some funky entangled state, right? This is an entangled state of all the possible implementations of 5, but they're all associated with just a single qubit up here. So you're basically building a quantum circuit, if you like, that when this is 5, it will construct a quantum superposition of a whole bunch of things that look like 5. It's interesting, in these particular cases, these particular kinds of deep learning circuits, as I've described them, you can use them in 2 ways. One, you can say, what do you think a 5 should look like? So it will operate in generative mode, where you put in 5 up here and it will generate things that should be like 5s. Or you can operate it in a recognition mode, where you put something that is a 5 down here, and the 5 neuron or 5 qubit is supposed to become a 1. It's supposed to light up. So naturally, I won't be able to describe all these methods here, but I urge you, we have quite a few papers on this topic now, and that map out how that you can get these exponential speedups. So what I'm going to do is I'm going to tell you what you need to make this happen, and I'll describe one of these algorithms. I think maybe I'll describe the principal component analysis algorithm, because actually principal component analysis is maybe the absolutely most common machine learning technique. Okay, so quantum data. So how do we actually turn our data to a quantum mechanical form where we can do this? It sounds crazy that one can actually do this, but I'll describe it now how this happens. So what we want to do is the following. So we want to take our classical data and we want to map it to a quantum mechanical state. So the point here is that if this belongs to something, now I'm going to actually, quantum mechanics naturally gives us complex numbers, so let's have our data, we allow it to have complex numbers as well. And then if this is so this is a very high dimensional vector space, that's the idea. We're going to want to construct a quantum mechanical state whose amplitudes, these amplitudes are the components of this vector. Okay, so this is equal to, you know, V1, V sub J1, V sub J2, up to V sub JD. So we want to construct a quantum mechanical state whose amplitudes are the same as the entries of this vector. That's what we want to do. Now, this is actually the most important point right here, and it will explain why we get a speed up. So if D is equal to 2 to the little n, then this is a state of n is equal to log to the 2d qubits. So here I have a classical piece of data. It's a vector in a high dimensional vector space. I require d numbers to specify it. So it takes order d bits, where the order just tells me what degree of precision I need to specify these numbers to. This takes n is equal to, I already wrote it so I don't have to write it again. This takes n is equal to log the base 2 of d qubits, and what that means is that I have an exponential compression in the representation of the data. So this is the main point, okay? So, and I'm going to go over it in a little bit of detail, but if I have vectors in my classical case in a d-dimensional space that requires order d bits of information to describe, then the quantum mechanical version of those vectors actually can be written down in a quantum state of only log d qubits. So the quantum states give you an exponential compression of the actual data. I'll describe how to do this in just a second. We need what's called a quantum random access memory, or QRAM. But before I describe how to do this, let me actually then just point out about how this particular feature explains why we can do all these machine learning problems exponentially faster. But is this clear? For the quantum, okay, first of all, quantum people, does this make sense? Let's give me some feedback. I know it's tough here in Japan. You got to like nod your head, or if you don't like it, you can shake your head. Are you okay? People are okay about this? I mean, the whole point is that, you know, quantum mechanical systems, if I have n qubits, then they live in a 2 to the n dimensional complex vector space. So the amplitudes actually can encode a very high dimensional vector. Okay. Okay, are we okay? This is one of those speak now or forever hold your peace kind of moments here. So, if you haven't studied quantum mechanics, does this seem strange? This is just a fact about quantum mechanics. Yeah, I'm afraid that it's the kind of thing you just have to sort of suck it up, you know. It's just the way things are. Quantum mechanics, the states of quantum mechanical systems are vectors in very high dimensional vector spaces. And if you have a small number of bits, then you just have an exponentially high dimensional vector space that they sit in. That's just the way it is. Okay. Okay, good. We're good to go. So, now let's actually compare, since we're at this stage, let's actually compare the classical versus quantum mechanical. So let's look at the classical version. Okay. And then let's look at the quantum version. So if I look at the classical, and what I'm going to tell you now is the computational complexity of the classical fast Fourier transform, classical algorithms for finding eigenvectors and eigenvalues, classical algorithms for matrix inversion. Okay, so the classical algorithm for fast Fourier transform goes as d log d. Right, this is, I mean, fast Fourier transform is fast, but not surprisingly, you have to look at all the data. So you have a d. The log d says you can do it in a very shallow circuit. Okay. All right. Now they're going to give us a little announcement, right? It's like.
No, this is just the beginning of the lecture.
Just the beginning of the lecture, I understand. Okay. Finding eigenvectors and eigenvalues. All right, well, the only way I really know to find eigenvectors and eigenvalues is basically Gaussian elimination. Gaussian elimination takes time, order d squared for a non-sparse matrix, or order s d squared for a sparse matrix. And the same is true for matrix inversion. Actually, for sparse matrices, you can get order d log d, but in general, sorry, order d cubed. This is a d cubed, excuse me. In general, all of these algorithms take time that is either all quasi-linear in d or some small polynomial in d squared or d cubed. And if you look at the quantum version of these, the quantum Fourier transform famously takes time order log d squared. You know, I have n qubits, takes time order n squared, which is log d squared. Finding eigenvectors and eigenvalues takes time, also takes time, order log d squared, and matrix inversion takes time, order log d cubed. So all of these famous linear algebra, basic linear algebra subroutines, which in MATLAB are called the BLAS, the basic linear algebra subroutines. So there's this feature that these basic linear algebra subroutines are exponentially faster on a quantum computer than they are on a classical computer. And the reason is that actually these quantum states take, you know, they have an exponentially fewer number of bits than the classical states. And so now that I've told you this, it shouldn't actually come as much surprise that we can actually do some of these machine learning algorithms in a quantum setting, that we can actually do them exponentially faster than we can classically. But before I show you how this is done, let me just point out that this is actually very important, because think of how big some of these vectors are. It's very common to have vectors that are a terabyte, you know, 10 to the 12 bits. This is a very reasonable size for a database these days. That's actually kind of a small database these days. Okay, d log d, that's getting to be kind of tough. We're talking, you know, around 10 to the 13, 10 to the 14 operations. That's quite possible, but it's going to take a while. D cubed, d squared, forget it. You know, d squared is already Avogadro's number. There aren't any supercomputers that can perform Avogadro's number of operations in a reasonable period of time. That's just the way it is. D cubed is, you know, 10 to the 36. That's pathetic. You're never going to be able to do that on a classical computer. It's just not going to happen. So, you know, even for reasonable sized data sets, these kinds of operations are actually going to be hard to do classically. And in fact, this is why people, in fact, why they don't do that. They try to say, oh, well, let's pre-process the data in some way. Let's just the kind of thing that you were talking about. And let's try to be smart about how we're doing this, and maybe we'll do better, because they actually can't even do something as simple as matrix inversion or finding eigenvectors and eigenvalues. So you've got to be really careful. This is why, for instance, Netflix, why they only do their principal component analysis every day, because it takes them a whole day to do it. Right? They would like to do it faster, but they do it every day. Okay. So because remember that 2 to the 10th is equal to 10 cubed, right? Plus change, 1024. So terabyte is log of 10 to the 12th is log to the base 2 of 10 to the 12th is 40. So 40 squared, 1,600 operations. 40 cubed, you know, 50,000 operations or 60,000 operations. Terabyte of data, you know, so, and it's on 40 qubits, right? So you can if you can map the system to a quantum mechanical state, you map a terabyte to a quantum state with 40 qubits, you can perform the manipulations in a few 10,000s or 10,000s of operations that you can do. Or that you ought to be able to do on the kind of quantum computers that are going to show up in the next 5 to 10 years, which are going to have 50 to 500 qubits, be able to perform tens of thousands of coherent operations. So this is doable. So this would be good. This would be a very good use for a small-scale quantum computer because you don't even necessarily have to use error correction because you've got such an excellent compression and because you've got these exponentially faster algorithms. So for people who are worried about quantum computation being difficult because if you want to factor large numbers, you have to have huge amounts of actual physical qubits because you're using massive amounts of error correction. This is stuff you might be able to do without having error correction. So that's what's going on here. Is this reasonably clear? I'm taking silence.
So here you're using the digital computing, quantum computing.
Digital quantum computing. Yeah, that's right.
Rather than this deep learning things
That's right. This is digital quantum computing, not deep learning. Right. That's right. The deep learning, so with the deep learning, the quantum deep learning, people can build these devices. They have thousands of qubits in them. But it's not clear that they actually provide an actual speed up. Okay. But it's worth trying it out to see what happens, because there they even have these devices. So this is digital quantum computation with a quantum random access memory.
But you're going to talk about readout. What's the importance of readout? Or?
Well, the nice thing about these kinds of algorithms is that all these things like finding eigenvectors and eigenvalues or matrix inversion. For instance, in the support vector machine, it's a big matrix inversion problem. You construct what's called the kernel matrix for the data. You invert this matrix. You apply it to your new point, and this allows you to classify it. So the readout in such a system, remember this was a classification. Does it go to cluster A or to cluster B? Right? So the readout is just a bit that says, hey, it belongs in cluster A. Right. I mean, people criticize the quantum matrix, the quantum matrix inversion, where I construct a quantum state, which is, A inverse times some other quantum state. But you never have to read out all these components for these things.
Oh, never have to read out. But you have to read out each qubit, basically, to at least the qubits that represent the
right. Or you have to do things like look at inner products between a vector and the vectors that you construct. So for instance, you construct this vector, and then to figure out to classify some other vector over here or there, you need to just take the inner product of this vector with your vector you're trying to classify.
So
that's not so hard.
If you draw a quantum circuit,
yeah,
you're going to have the first part of the initialization, and then you have to input data, so FFT, and move on.
Yeah, exactly. So in fact, the output part is relatively straightforward. The harder part, and I'll talk about this very briefly, is this input. So you have this data, your data in a classical form. So you're given data in classical form. I don't have one with me right here, but normally I carry around a CD with me. Actually, the CD I carry around is called "Is the Bible True?" Because somebody sent me a CD called "Is the Bible True?" I've never cracked it open, but it's been very useful for me to demonstrate this. So imagine I'm holding a CD in my hand. So this step, so this quantum random access memory is a very important one. So let's actually look at this quantum. So in a random access memory, you want to have something that says, here is the value of the memory register. Well, let's just do the classical version of this. So you're given give me the value, the data, I'll call it just B sub r, in the rth memory register. So, here is memory register 1000111110101, a 40-bit for a terabyte of memory, and the data in the rth register. So this is classical RAM. That's ordinary random access memory. And in QRAM, what you want to do is you start out with a quantum state that represents this memory register. And then this is going to be mapped to something that retrieves this as a quantum state. But the important thing about the QRAM is that it also is going to work in quantum parallel, so that I can preserve quantum coherence. This is QRAM. Now this is hard to build because, of course, even though this is only 40 qubits, this could be much less than 40 qubits, this could be 1 bit. You do have to do this in a way where you access this classical data. But actually I claim, in fact, it turns out rather surprisingly that accessing classical data in a quantum mechanical fashion is relatively straightforward. So suppose I have this CD. You're going to have to imagine me holding this CD right now. CD is an array of billions of little mirrors. In fact, and absence of mirrors. So presence of a mirror is 1, absence of a mirror is a 0. And the way you read this classical data normally is that you spin it past a laser and you look at the reflections off of it. So if you see a reflection, it's 1. If you don't see a reflection, then it's 0. But in fact, this information can be encoded in a quantum state of a single photon in a very straightforward fashion. Let me take a single photon. I produce it with a laser. I have a lens. The lens expands the wave packet of the photon, so that now this whole photon in quantum superposition bounces off the entire CD at once. Now each of these mirrors on the CD defines a mode of the electromagnetic field, and after the photon has bounced off the CD, it is in a quantum superposition of all the places where there were mirrors. In other words, its quantum state of the single photon is a vector that actually encodes the entire classical information on the CD simultaneously. It's kind of amazing, but not that hard to do. The tricky part is actually doing it in a digital fashion. So if this is in a set of qubits, I want to be able to actually, get a quantum superposition of each memory register correlated with the value of that photon. Now, I don't actually have time to talk about this today, but I will tell you that there are methods for doing this. We actually have patented it. Came in a kind of a funny fashion because we came up with this design for a quantum random access memory because I met Sergey Brin and Larry Page at this dinner in Monterey, California in 2003 or 2004. The dinner was called the Billionaire's Banquet. And you might ask what I was doing there. The answer is, I kind of like the guy who jumps out of the cake wearing a bikini, right? The entertainment for the billionaires. Anyway, it turns out they were very interested in quantum computing, so we came up with something we wanted to call, in the end, we came up with something we were going to call Krugel. Right? So they asked me to come up with something that dealt with the quantum internet. So we said, oh, well, do something that's called Krugel. By the way, the logo for the Quantum Artificial Intelligence group at Google is this. This is Google. If the quantum people know that these are Dirac brackets, if you haven't seen them before, it just means that whatever inside is quantum mechanical. So I call this first quantization, and this is second quantization. Anyway, it was, we came up with this idea. In fact, I recall talking about this here like 5 or 6 years ago, maybe 7 years ago now when we came up with it. Came up with this idea where we showed that if you had a quantum random access memory, then you could do the following. If you stored a database on it, then someone who accessed it using a quantum random access memory could make a query to the database, get the answer, and the person who owns the database would never know what the question was. So you could actually you could search Google's database with complete anonymity without them never knowing what you were asking. It was be a great thing. And I think actually most of the people who were, but I will tell the rest of the story. So we came up with this, we patented it. By the way, it's actually pretty easy to figure out what they do. So quantum mechanically, this relies on the no cloning theorem. If you make a copy of something, you mess it up. So the way that this Krugel works is that you send a question to Google in the form of a quantum state. They send you back the answer, but then they send you something else, and because they send you this something else, you can tell for sure after it's all done that they don't know what the question was. So what do they send you in addition to the answer? You send them a question, they send the answer, they send you something else, and now you know for sure they don't know the question. What's the additional thing they send back as well as the answer? They just send you the question. And then if they made a copy of it, you can tell from the no cloning theorem that they made a copy of it. So you can be sure from the laws of quantum mechanics that they answered your question and they don't know the question. So actually this took us about 3 or 4 years to figure out, and then after, because this was an alarming thing, and so then I met them again at this other boutique conference in Napa Valley, and in the hot tub at 2 in the morning I like pitched them on it. It's like, okay, you guys want to buy this? And they said, very interesting, very interesting. But they came back the next day and they said, oh, Seth, we're so sorry, we can't buy this from you. I said, well, why not? It's like, you just bought YouTube for $1 billion, what the hey? And they said, yeah, but our business is based entirely on knowing everything about everybody, and we couldn't possibly buy technology which would mean that we would know nothing about anybody. And I said, look, you're looking at this the wrong way. You're in big trouble with the European Union because you're spying on everybody all the time. So I'll tell you what, if you're worried about this competition with your core business, just like, you just give me $10 million and I won't do anything. Okay, so no competition for your core business. Then you tell the European Union, the European Court of Justice, hey, we're so committed to privacy, we've invested a substantial sum of money in a technology that will allow people to have complete privacy guaranteed by the laws of physics. So no, the European Court of Justice is happy, that means you're happy and I'm really happy. But they didn't see it that way. And since then they spent hundreds and hundreds of millions of dollars actually fighting the European Court of Justice on this. They really should have taken my offer back then. Okay. I'm pretty much out of time, but let me tell you how this, this quantum PCA algorithm works. So here we have these vectors. These are our data. We construct the matrix, which is just the sum over J, Vj, Vj. This is the covariance matrix of the data. You see that this is actually just the density matrix for the data. Okay, I'll just say 1 over the number of data pieces. So you can actually construct the covariance matrix of this data merely by putting the data in quantum mechanical form and then sampling from it. This gives you a state, a quantum state, which is the density matrix of the data. It's also the covariance matrix of the data. Now we want to find eigenvectors plus eigenvalues of rho. Remember, that's what principal component analysis is. So rho is equal to the sum over k, pk, kk. And the idea is that if the low rank, if rho is low rank, there's only going to be a small number of these pk that are large, that are close to 1, order 1, and they'll correspond to the corresponding eigenvectors. We want to find those. So how do we do this? So note, if we can perform e to the minus I at acting on some state psi, so if we have a matrix that is Hermitian and we can treat it as a Hamiltonian, then we can actually take psi with something 0 and we can map it into the sum over k, psi k, k, ak, where this is the eigenvector of A, and this is the eigenvalue of A. So if we can actually access a matrix in this dynamical form, then we can actually decompose any state into its eigenvectors and eigenvalues. This is normally called the quantum phase algorithm. It was invented by Kitaev, but I actually want to just point out to you that this is just von Neumann measurement. So this is just the von Neumann pointer variable model of measurement. Von Neumann pointer variable model of measurement dates to 1930. It's in the last chapter of von Neumann's famous book. He simply points out that I can model measurement by having the quantum state that I'm looking at, another variable which is the pointer variable, and then I correlate the pointer variable with the value of the eigenstate of for each eigenvalue of A, I correlate the pointer variable becomes the eigenvalue. So not only is this a well-known technique, it's been well-known for almost 100 years. I better finish up, but I'm almost done. So you see what we actually want to be able to do is we actually want to be able to take e to the minus I rho t, acting on some state psi. So we'd like to, if we can construct copies of a density matrix, if we have many copies. So what's our goal here? So if we could somehow, given copies of rho of this density matrix, we could actually, in some sense, turn it into a Hamiltonian and exponentiate it, then we'd be able to find its eigenvectors and eigenvalues just using conventional techniques. But I claim we can do this. So if I take e to the minus I, swap delta t, and then I have rho tensor sigma, and e to the I swap delta t. So this is just the swap operator. I have two registers, A and B. I take a copy of rho. I want to apply this to this vector, this density matrix sigma. And I claim that if I can just do a swap operation, and I trace over A. This is amazing chalk, by the way. I'm really, really enjoying this. That's why I'm talking longer and longer and longer. I want to prolong this moment of using this magical talk. Okay, so I just do this infinitesimal swap. I throw away the first register. I find this is equal to sigma minus I delta t, and then the commutator between rho and sigma plus order delta t squared. You just have to work this out. It takes a little bit of algebra to make it happen. Yeah, this is one of these, like, you just got to suck it up kinds of things. And quantum mechanics is full of these moments where you just got to suck it up. So here you just got to work this out. And you'll find that this is the case. But now you may notice that this is actually equal to e to the minus I rho delta t sigma e to the I rho delta t plus order delta t squared. So in fact, we can treat rho as a Hamiltonian. But if we have just one copy of it, it's only for an infinitesimal amount of time. But then we just do it again and again and again with new copies of rho each time. So we can actually exponentiate rho. This is a sneaky trick. Kind of fun to do. People are doing this experimentally now. And now actually you see what happens is, okay, we can exponentiate rho. We can treat it as a Hamiltonian as long as we can construct multiple copies of it. Well, we construct multiple copies of it just by sampling, and then we just do quantum phase algorithm or von Neumann measurement or pointer variable operation, and that means we can indeed find the eigenvectors and eigenvalues of rho. So we can find the principal components of our data. So that means that we can perform quantum principal component analysis. And this is very useful because once you, again, principal component analysis is an extremely common technique. You can think of this as a way of summarizing the data. It's very useful for predicting future behaviors of data. Actually, I would like to mention that in the case where this is a very useful just quantum mechanical technique. Forget about quantum machine learning for the moment, this is an excellent technique for doing things like, suppose that rho is something that's coming out of an experimental apparatus. And my question is, oh, I've got these states in a high-dimensional Hilbert space. Is this a low-rank matrix or not? That's actually an extremely interesting question. And you can find this out by using this principle, this quantum principal component analysis. So this also has a very strong applications in quantum tomography, completely independent of data analysis. Okay. I'm over time. Let me just summarize. Machine learning, well, quantum mechanics describes how things behave at the smallest and most fundamental level. We have simple quantum computers now. We're going to have more complicated quantum computers in the future. They'll still only be, 50 to 1,000 qubits, but I mean, this is what's going to be happening over the next 5 to 10 years. What can we do with them? Well, very common use of classical computation is machine learning, finding patterns in data. There's a huge number of different possible machine learning algorithms out there. But when you unpack many of them, a very wide variety of them are simply about doing linear algebra on high-dimensional vector spaces. What is the dumbass intuition about why quantum machine learning should work? Well, quantum mechanics is all about linear algebra on high-dimensional vector spaces. And when you translate that into algorithmic terms, it means that quantum computers can do Fourier transforms, find eigenvectors and eigenvalues, and do matrix inversion exponentially faster than their classical counterparts. And these are, in fact, these are, in fact, effectively the known, all the known quantum algorithms that give you exponential speedups are variations on these kinds of algorithms here. So if you can construct a quantum random access memory that maps classical data into quantum states, that gives you an exponential compression of the representation of the data. And this is often enough to be able to extract all kinds of interesting features of the data. So I showed you how you do this for principal component analysis, but you can also use it for these support vector machines, constructing optimal separating hyperplanes. You can do it for cluster analysis. And actually, after several years of effort, we were able to show that you could do it for this topological analysis as well. So you can actually reveal the topology of your data set exponentially faster than you can using a classical computer. And it's a fun topic. I invite you to come up with your own quantum machine learning algorithm simply by going out there and saying, hey, I wonder what machine learning algorithms there are out there. And then by gum, a lot of the time it turns out you can quantize it. So it's a fun thing to do. Well, what's the rationale for doing this? So there's two rationales for doing this. One is that, okay, we know for a long time that, that in order to get grants, you either have to talk about big data or you have to talk about graphene, right? So graphene, the material of the future, so that gallium arsenide has a friend in being the material of the future, and now it's not lonely. So one rationale is to write a paper called graphene-based, or write a grant proposal called graphene-based quantum random access memories for analysis of big data. Right, it's bound to be funded. The second rationale is for things like these financial time series. We feel that, back in the 2007, 2008, a bunch of, when the world economy almost crashed, that this was done effectively by a bunch of unemployed string theorists, or string theorists who were employed on Wall Street to, make fancy models of financial systems. Because of course, if you want someone who is mathematically adept and really has their feet on the ground and a strong empirical sense of the world, you would hire a string theorist because, well, never mind. We feel we missed out this in quantum information. So we feel if we could, construct the right quantum financial algorithms, that we could, rather than merely removing trillions of dollars from the world economy, we could destroy the whole thing. So, and that's the end. Thank you.